Thanks. Yes, so this is a work by Nicola, Galesi, Leszek, Kolodziejczyk, and Thapen on polynomial calculus space and resolution width, and I'll try to make clear in a minute what this is all about, but just to add the caveat that this is with somewhat short notice. This is a deep paper that I don't fully understand myself, other than that I love it because it's doing new great things. So, you know, we're in this together. Let's see how far we can get, and I'll try to make some sense of the slides. So let's just jump right into it. This is about proof complexity. So we're proving unsatisfiability. So we'll start by doing CNF formulas. We want to prove that a CNF formula is unsatisfiable. We'll use the classic resolution proof system. Every line in the proof is a clause, which is either an original input clause or axiom from the formula we're trying to disprove, or it's derived by the resolution rule that says that if I have derived previously C or X and not X or D, then by simple case analysis over X, I know that C or D must hold. So I apply this rule over and over again until I derive box, the empty clause, which is contradiction. Okay? This is the resolution proof system. We're going to be even more interested in the stronger polynomial calculus with resolution proof system, where we're reasoning about polynomials. So now the input is a bunch of polynomials, which we think of as polynomial equations. So sometimes we'll add that the polynomial equals 0, and sometimes it's just understood from context. The polynomials live in a ring over some field with variables x1 up to xn and x1 bar up to xn bar. These are formally distinct variables. Okay, and then we have now every line is a polynomial, which might be either that x squared minus x is 0, that enforces Boolean 0, 1 values, and that x and the negation of x take opposite values, so that we make sure that these formally distinct variables respect the meaning of negation. And then we just say, well, if two polynomials p and q are true, then clearly any linear combinations with a and b living in the field is also 0. And if the polynomial p is 0, then any variable x times the polynomial p is also 0. And we derive that there is no common root to these set of polynomials by deriving the constant polynomial 1, which very rarely evaluates to 0. Okay? So, and why do I say that this is stronger than resolution? Well, it turns out that there's a straightforward translation of clauses into polynomials, in fact, into monomials. If I have x1 or not x2 or x3, then I just translate it into x1 bar times x2 times x3 bar and want this to be 0. And then it's not so hard to show that anything you can do in resolution, you can do in polynomial calculus also, and polynomial calculus is in fact exponentially stronger. Okay? Good, so these are the proof systems we care about. And in fact, let me describe slightly more carefully what we mean by a proof, because we're, as was hinted to by the title of the talk, we care about space. So what do I mean by the space complexity of a proof? So the normal, like on the previous slide, we had proofs in the way we write them in papers, right? A full proof from beginning to end. But now space sort of models the way I would actually teach the proof in a lecture setting. So there's a whiteboard on which I present the proof. And at any given point in time, I have stuff on the board, and I have stuff that I have not yet presented on the board. And then, you know, I have good board techniques. So once I use the lemma and I don't need it any longer, I erase it. Okay? So in some sense, the space complexity asks like about sort of the locality of the proof, how complex it is. So formally, we have, at every point in time I, we have a snapshot of our memory, what's on the board. That's mi. And this is in resolution. This will be a bunch of clauses. Okay, and we start with the board wiped out, empty and clean. We end with contradiction on the board, like the final result. And then at every point in time, what can we do to move from time I to time I plus 1? Well, either we can look at the formula. We have it written down on a like read-only slip of paper and write down an axiom clause. So we just, you know, this is a clause of our formula. We copy it to the board. Okay? Or we can apply the inference rule, which is just we look at two clauses on the board and we apply this resolution rule, this case analysis over the variable x. Or using our board technique, we delete stuff that we no longer need. Okay, does this make sense? Good. So, and sort of this, the way I wrote it here, or the way they wrote it here, it's defined for resolution, but of course it's like, this is a very generic definition. You can do the same for polynomial calculus. Now, like every m will just be a bunch of polynomials, and then you can download new input polynomials, or you can apply the different inference rules, and again, you can erase polynomials. Okay? Good. So what are the complexity measures that we care about? Well, we care about space mainly, but also about width and degree, and that will become clear in a minute why. So what's width? The width of a clause is just the number of literals in it, the size. Okay? And the width of a proof is then just go over the whole resolution proof, take a largest clause, that's the width of the proof. Okay? And the space of a memory configuration is just the number of clauses. Similarly, the space of a whole proof, just take the max over all the configurations. So note that I'm charging you 1 unit of memory now per clause. Okay, so you might say that this is a bit generous. So there's also a finer measure that is total space, where I now charge you actually 1 unit of space for every literal appearing on the board. Okay, so these are the two measures that I want you to remember. Space, which is counting clauses, and total space, that is counting total number of literals. Okay? And in polynomial calculus resolution, in PCR, the analog of width is degree of a term. Degree of a polynomial is just the total degree of all terms. And then you look at the proof, like the largest degree that you see, that's the degree of the proof. Okay? That's like an immediate analog of width. For space, again, clauses translate into monomials. So in polynomial calculus, it's natural to count the number of monomials. So a space of a configuration will be the number of monomials in it. And again, the proof space is just the largest number of monomials that we see on the board at any given time. And then, of course, once we have these measures defined, we can just fix a formula, and we can minimize over all possible proofs of it, and for instance, define the space in resolution of refuting the formula F, of proving that it's unsatisfiable, as the minimum proof space of any proof. Okay? So, and we want to study these measures and understand how they're related. And it turns out, somewhat surprisingly, that width and degree are surprisingly useful measures that give a lot of information about other measures. It gives information about proof size, which I won't even talk about to save time, but also about space. So there's a beautiful paper by Atserias and Dalmau. So this is the Albert Atserias that had the best paper award at this Fox. But this is an earlier beautiful paper of him. So that says that if, for a formula F, I can prove that at some point in time, the proof needs a wide clause with W literals, okay? Then that implies that in any proof, at some point in time, I need W distinct clauses in memory. Okay, this is somehow not at all a priori obvious that it would be true, but it's true. And then this was strengthened by Bonaccina, who said that if I, at some point in time in a resolution proof, will need a wide clause of width W, then in fact, at some point in time, I will need essentially W clauses of this width W, okay? Meaning that the total space is the resolution width squared. And in fact, like most space lower bounds, you can then get in this way via width lower bounds. So a natural question, because it turns out that if you follow the literature on polynomial calculus and on resolution, like there are close parallels between results, only that the results for polynomial calculus are much harder to prove. Okay, so this raises the obvious question like, okay, if I plug in degree here and polynomial calculus space here, does something similar hold? Is it the case that polynomial calculus degree lower bounds polynomial calculus space? This is like the starting point of this work. In fact, you can ask for something slightly stronger. Namely, if the polynomial calculus degree that you require is high, then this immediately implies that the resolution width is also high. Okay? But this is a one-way thing. So we can, assuming that the resolution width required is high, is like a weaker assumption. And we can ask, is it maybe even the case that high resolution width implies high polynomial calculus space? Okay? And this has been conjectured to be true. And then there was we had a paper where we proved a kind of, not quite this, but we said that, well, if the width of a formula is large, and if we sort of modify it in a syntactic way, which I won't get into, then this holds. So this is some kind of circumstantial evidence, but really not at all what we want, because these two formulas are actually different. Okay? So now I can state what is the main contribution of this paper. So this is indeed resolution with does lower bound polynomial calculus space. So if I work in the very simple resolution proof system, and I'm able to prove a resolution with lower bound on the clauses, then this immediately carries over to the much stronger setting where I'm allowed to do polynomial reasoning and I'm measuring space. Okay? With a small hitch that we're losing a square root here. So if there's a polynomial calculus refutation in space S, then there is a resolution refutation with S squared. So the result for resolution was S and no square. So, and in particular, as I said, so because width is like a weaker assumption, this in particular implies also that lower bounds on degree imply lower bounds on space. But again, there's this square root loss. Okay? So in what remains of my time, which is already vanishing far too quickly, I'll try to give you some flavor of how the proof goes. But I'm actually not going to be able to say anything meaningful about the polynomial calculus proof. So I'll focus on another nice consequence in this work, which is about resolution, and which sort of conveys some of the main ideas. Okay? So how do you prove a space lower bound in resolution? Well, most proofs go like in the following way. So assume by contradiction that there is a proof in space B, using at most B clauses. So I'll do a proof by contradiction by maintaining a partial truth value assignment for every time step. And this partial assignment alpha sub I satisfies M sub I. Okay? And hence, in particular, M sub I definitely doesn't contain contradiction. And somehow, the way I do this inductively, and so for every new derivation step, I update my alpha sub I. And when I do this, it's very important that alpha sub I, this partial assignment, is not too large. It's upper bounded by this current space. Okay? So it should be clear that if I can do this, then I have a space lower bound. Okay? Turns out that there's actually another way of doing this where you sort of work from the end. So this is like by forward induction. But you can also go by backward induction by sort of interpreting this technique in a slightly different way. And one of the key contributions of this paper is to combine both forward and backward. So we're going to start from the beginning of the proof and satisfy configurations. But then simultaneously, we're going to actually start from the back of the proof and falsify things, and then we'll meet somewhere in the middle, and a beautiful contradiction will ensue from the assumption that there was a small space proof. Okay. And a key absolutely key definition here will be that of an Atsiras-Dalmau family, which is a combinatorial characterization of what a space lower bound is. So if there are no small, what the width lower bound is, if there are no small width resolution refutations, then sort of there are fake truth value assignments that locally look just fine. So basically you should think of this family H as a family of partial assignments that say that no, the formula is satisfiable. And all these partial truth value assignments are small, they're downward closed, and I can extend them so that if I have a small assignment and you're asking about, well, in your satisfying truth value assignment, what do you assign to X? Then I can extend it to another beta in the family that does assign X, and all of these truth value assignments in H never falsify any clause. So as long as we're in small width, I can always like come up with an alpha that satisfies everything you've seen so far. This is somehow the intuition, okay? And in fact, this is an exact characterization. There is no resolution refutation in width W if and only if there is a family with parameter W plus 1. But this is like a paper, so this is not supposed to be obvious. Good, so now, so what I want to tell you about, if I have the time, is a corollary of this paper is that the fact that total space is width squared. There's a beautiful, simple result that follows from this, the technique in this paper, from this like forward, backward thing. So let's prove this. Total total space is at least width squared, formally I'll say that suppose that a formula has a proof where every configuration has at most s clauses and the width is at most m, well then there has to be a narrow refutation, namely the width is at most 2m plus s. Okay? So this is like, in particular, this implies that total space is width squared if you think about it. So let's argue by contradiction. Let's say that a clause is narrow if it has width at most m, and wide if it has width greater than m. And suppose, again, argue by contradiction, so since there is no width lower bound, then there is a family with parameter 2m plus s plus 1, where you can play this locally consistent game. Okay? So now we'll start at the end of the proof and find small partial truth value assignments in this family that screw up on narrow clauses, on small clauses. Such assignments certainly exist because the final proof contains contradiction, and that's a very narrow clause, and all assignments falsify it. So let's just go backwards in the proof to like the last point in time where some alpha in H falsifies a narrow clause. Fix it. That's M sub j. Okay? There certainly exists. Again, like worst case, it's this guy. Definitely exists. Okay? That's the okay. And now let's go one step further. Since this C is false, it's not an axiom, because our partial assignments never screwed up axiom clauses. So it's derived by the resolution rule, from C or X and C or not X, say, just to simplify. And then I extend alpha to an alpha prime that falsifies some wide clause. Okay, so now I've showed that there is some M sub j plus 1, where some partial truth value assignment in my family falsifies a wide clause. Okay, let's keep that in memory. Good. Now I'll make a forward pass, and I'll use my partial truth value assignment to satisfy clauses. But I only focus on the wide clauses. I ignore the narrow clauses. Okay? And let M sub I be the last point in time when I can satisfy all the wide clauses in memory. Okay? There certainly is such a last time, because M sub j plus 1 is a point in time where this is no longer true. This is what we established. So let's look at M sub j, and now we're close to a contradiction, and I'm going to simplify a little bit. But so there is some clause D that is wide and that is not satisfied by any partial truth value assignment that I have. Okay, but it was derived somehow, and it's wide, so it can't be an input clause. It can't be an axiom. So let's suppose for simplicity that it's derived from D or Y and D or not Y. This is a wild oversimplification, but it's like in the paper you can see how to do it properly. But then now, since they are appearing in earlier configurations, they are actually satisfied by some truth value assignment in my partial family, which is extending the truth value assignment that falsified this narrow clause C, which I forgot to say. Sorry about that. Anyway, so since this partial truth value assignment satisfies both of these clauses, then by soundness it has to satisfy this clause as well. But M sub I was maximal, so we're running into absurdity. What's the absurdity? Well, the absurdity was that there was no low width refutation, because that's what gave us the AD family. Okay? So we established the width lower bound. And now what's time?
You got about a minute and a half.
Wow, okay. So let me just say something very, very brief. Like, now we want to do this for polynomial calculus. What's the problem? Well, one key thing, there were like two key steps. There was this backward pass, forward pass meeting in the middle. That's one. Two, we were focusing on satisfying wide clauses, but we needed to do so very efficiently. We took like one literal per clause in order to stay within the budget of our family. Okay? Both of these things fail for polynomial calculus. Namely, to satisfy like monomials, suppose we have a polynomial 1 minus some high degree term. We want to fix this to true by setting only one literal, but clearly that's absurd, because in this polynomial you had to set all of them. There's no way we can afford that. We'll run out of our budget immediately. Okay? And also, just finding one interval doesn't work. So what we need to do is, firstly, we need to do like iteratively find smaller and smaller intervals, and we use something called, or they use something called forcing, where you don't actually fix things to true, but you you say that an assignment in my family forces something to true if there is no extension of this assignment in the family that sets it to false. And I think that's what I basically have time to say until before Ryan cuts me off. So, OK, let me try to say this. So what's the consequences? Well, we established that width in resolution and space in PCR, we saw that these are connected. We got a very simple proof of this resolution with lower bounds, total spaces width squared. It's definitely a new technique. I think like this is a paper that I want to read and understand better. I think there much more things can be done with it. We get new lower bounds for it. We get simpler lower bounds. We get a separation between size and degree and space that is independent of the field characteristic. And the main question, I guess, is, are these bounds tight? Okay, and what I mean by this is like, is the technique tight? Do we need to lose the square root? Okay? It's for all the concrete examples that we have where we now get like square root and lower bounds, the intuition is very strong that this is just showing that actually like the right bounds should be linear. We just don't know how to do it. Okay? But it might be that, yeah, for all of these concrete formulas that they're mentioning here, maybe the right lower bound should be linear, but maybe in general there is some other CNF formula for where really this square root loss is essential, and we have no idea. And I guess that's it, yes? Thanks a lot.